begin by saying that summarize the first lecture. So in our thing, we kind of noticed that the ring of integers is a subset of the rational number field, which in turn is a subfield of the field of real numbers. We know this from our high school days. And the field of real numbers, R, is constructed from the field of rational numbers by using the usual distance function given by the usual absolute value function. That means we take Cauchy sequences of the rational numbers and then take the limit of all these things and throw them in, and then it turns out you get the real numbers. But the Cauchy sequences, the measurement of distance is the usual absolute value. And last time we talked about for each prime p, we can construct a metric on the rational numbers, and then we can complete the rational numbers with respect to this p-adic metric, and this gives rise to the field of p-adic numbers. So you get a whole infinite collection of fields, QP, one for each prime p, in which the ordinary integers and the rational numbers are sitting. So in many ways, when we say analysis and talk about the study of real numbers, we're only looking at one line of the spectrum. And I kind of said this last time. But here now we get a whole spectrum of fields, one for each prime p. And Ostrowski's theorem tells us that these are the only ways to metrize Q, essentially. So any other metric you put is equivalent to the one that you've created by this methodology. So this gives us a more colorful view of the world, like the rainbow, Indradhanush, as they call it in India. A rainbow, a kind of a whole colorful spectrum of fields. Now, in this particular lecture, we'd like to talk about Kummer congruences. So last time we introduced Bernoulli numbers and the p-adic norm on the rational numbers, and completing the rational number field Q with respect to the p-adic gave rise to QP. And one can extend the p-adic norm to QP and show it's complete with this extended norm. We also talked about this last time. But in a sense, even though p-adic numbers were discovered in 1897 by Hensel, as I mentioned last time, the seeds for these ideas go back at least 50 years earlier, as I will try to explain today. In 1851, Ernst Kummer discovered important congruences for the Bernoulli numbers, and its p-adic significance only became apparent in the 20th century when Kubota and Leopold realized that they signal the existence of what can be called a p-adic Riemann zeta function. So this is an interesting idea. The theorem of Kummer is very elementary, and I'm going to prove that today. And but the interpretation, the p-adic interpretation of Kummer's 1851 work came much later, in 1964, actually, to be precise. So we'll try to move towards these ideas by the end of this lecture. And we'll first review briefly some of the results proved last time that are needed for today's lecture. So some properties of the Bernoulli numbers. Remember last time we talked about the summatory function, sk of n, which is basically 1 to the k plus 2 to the k plus n minus 1 to the k. And we showed that you can write the formula for the sum of the kth powers in terms of the Bernoulli numbers, this particular formula here. And our goal now is to derive the Kummer congruences and lay the foundations for p-adic interpolation of the Riemann zeta function. Now, we'll say that a rational number a over b with a and b co-prime is p integral if p is co-prime to b. That means there's no p in the denominator. So we'll say a rational number with no p in the denominator, it will be called p integral. And given any rational number, we mentioned this last time, we're given any rational number r, we can write it as p to the u times a1 over b1, where a1 and b1 have nothing to do with p, and this determines u uniquely, and we define ord p of r to be u, and sometimes we also write vp of r to designate u. So we now begin with the following theorem. If p is a prime number, any prime number, p times b to the k is p integral. And we will prove this by induction on K. And we go back to that formula 2.1, and we will set n equals P in that particular formula. And we write it as, well, Sk of P is equal to, take the first term corresponding to I equals 0. You'll see that it's P times B sub K. And then take the other terms going from 1 to K choose I, P times B, K minus I, P to the I over I plus 1. So I took P to the I plus 1 and wrote it as P times P to the I. And now you can see that we can use induction. Induction is a very beautiful method. You can see use induction and see that, for example, all these by induction are P integral. There's no P in the denominator. And this is certainly P integral because it's just a natural number. And therefore, this has to be P integral. That's basically the proof. So I will kind of, leave it at that, more or less. You just have to be a little careful and try and show that these are P integral also. And that's what I'm doing here. So once you get the idea, I'm sure everybody can clean this up a little bit and make sure everything is tidy. So I'll just leave the exercise that you have to show that the power of P appearing in P to the I minus 1 divided by I plus 1 is always non-negative. Basically, you have to show that the power of P that can divide I plus 1 cannot be too big. Usually, it's at most log I over log P. Okay, so I'll leave it at that as an exercise for you to do. Now, the denominator of a Bernoulli number, the previous lemma allows us to deduce an important fact about Bernoulli numbers. You will recall last time we said they were rational numbers. Now we will show that if you write your Bernoulli number as a rational number uk over vk with uk and vk coprime, then vk is actually square free. So this is an interesting property of Bernoulli numbers too. And the reason for this is if p squared were to divide v sub k, then it'll contradict the previous theorem. You see, if there's a square of a prime in the denominator, then when I multiply by p, I just proved p times b sub k is p integral. There is no p in the denominator. And therefore, you couldn't have had a square of a prime dividing vk. So that's basic proof. But these very small observations coalesce into a grand theory that hopefully will become apparent as we continue. Now we can sharpen the argument of our previous lemma to deduce that, in fact, not only is p times b sub k p integral, but p times b sub k is congruent to sk of p mod p. And the proof of that is also similar. We write sk of p as we did before, with the k equals 0, the I equals 0 term being here, and the I equal and the higher terms here. And when we do that, we find that by induction, everything else p integral. So I took out another p here. And remember that the Bernoulli numbers, the odd Bernoulli numbers are all 0. So keep that in mind. So that's why where the hypothesis k is even is used. So the I equals 1 term is missing here. So what primes divide the denominator of the Bernoulli number? Recall with our metaphor of viewing numbers as functions, this is tantamount to asking what are the poles of the Bernoulli number? So when we're talking about the denominator of a rational number, it's sometimes useful to think of it as poles, like you would for a rational function. This can be answered very precisely and was first done by von Stout in 1840. So this is why I said, some of the ideas, even though p-adic numbers were discovered in 1897, some of the groundwork for the discovery of the p-adic numbers was already being laid 50 years earlier. So this is what I always find fascinating. Anuradha mentioned last time that I'm a part-time philosopher. I'm fascinated by the process of discovery and how historically certain things happen to prepare the ground, as it were, for these discoveries. So I want to talk about von Stout's work in 1840. The proof is very elementary number theory, so it should be appropriate to this audience here. So before we do that, let's recall that a group of coprime residue classes mod P is a cyclic group. Now, any generator of this group is called a primitive root. So recall this fact. So what I'd like to prove now is if P minus 1 does not divide K, Sk of P is 0 mod P. And if P minus 1 divides K, Sk of P is minus 1 mod P. Okay, so let's look at this Y. So let G be a primitive root. And if P minus 1 does not divide K, we can look at Sk of P. Remember, it's the sum of the first P minus 1 kth powers, so the first P minus 1 numbers. And all the residue classes are generated by powers of G. So we can write Sk of P as a geometric series, mod P. And when we do that, we can sum this. We get G to the K P minus 1 over Gk minus 1. And we immediately see by Fermat's little theorem, G to the P minus 1 is 1. So the numerator is 0 mod P. If in the case that P minus 1 divides K, we find Fermat's little theorem says that sum is P minus 1. And it's congruent to minus 1, of course, mod P. So this is how you get it. Very simple, very elementary proof. Now, Won-Stout-Clausen theorem, apparently both Won-Stout and Clausen discovered this theorem in 1840 independently, but only Won-Stout gave a formal proof. But we still call it Won-Stout-Clausen theorem. For K even, the Bernoulli number, Bk, plus summation 1 over P minus 1 dividing K is actually an integer. So what does this say? Now, let's go back to our metaphor of trying to think of numbers as functions. And if we have a rational function, for example, and it's got poles, you remove the poles, then you have an analytic function. Something similar is being stated here. The only thing that can appear in the denominator of a Bernoulli number are those primes P, so that P minus 1 divides K. Not only is the denominator of the Bernoulli number a square free number, but we can actually tell what primes divide the denominator. And they are the primes P such that P minus 1 divides K. So using our metaphor, this says that the poles of Bk occur at primes P such that P minus 1 divides K, and these poles are simple. That means you're not going to have higher powers. So recall now, earlier we proved that if K is even, then Sk of P is congruent to P times P sub K. And that if P minus 1 does not divide K, Sk of P is 0 mod P. If P minus 1 divides K, Sk of P is congruent to minus 1 mod P. These were proved in the previous slide. I'm just trying to recall them. So now, in trying to prove the Won-Stout-Clausen theorem, if P minus 1 does not divide K, then your lemma 2.6 implies Sk of P is 0 mod P. So by lemma 2.5, the first one, P does not divide Vk. Because if it did, the denominator, P does not divide V sub K, because if it did, it would have canceled that P. And if P minus 1 divides K, then again by lemma 2.6, Sk of P is minus 1, so that by that lemma 2.5, we get our result P times P sub K is congruent to minus 1. Therefore, P necessarily divides V sub K. So this is a beautiful theorem, actually. All the primes dividing V sub K are precisely those primes P, such that P minus 1 divides K. Now, if P is 2, P minus 1 is 2 minus 1, which is 1, and 1 always divides K. So that means the denominator of any Bernoulli number will always be even. And then if P is 3, then 3 minus 1 divides K if K is even. And since Bernoulli numbers are really only supported at even subscripts, we find that 6 always shows up in all these things. So P integral for every, so we just finished proving that, and it's trying to make this remark that 6 always divides that. So now let's go keep this in mind.
I have a question.
Yes.
Yeah. So I wanted to ask if those set of primes have any relation with regular or irregular primes.
Yeah, you're jumping the gun. I will talk about regular primes later.
Do this set has any intersection or any inclusion relation with those?
Yeah, I'm going to come to that point.
Okay, sir. Thank you.
Yeah. So now we write our Bernoulli number bk as uk or vk, with uk and vk co-prime integers. And we've just shown right now that the denominator is square free and divisible by primes p, such that p minus 1 divides k. So my preliminary comment tells us that 6 divides v sub k. So now I would like to show that if we to try to understand these numerators and denominators, we will now establish this stronger congruence. If k is even, then vk times sk of n is congruent to uk times n mod n squared. So let's try and prove that. So we go back to that very elementary formula. Remember I mentioned the Aryabhata-Bernoulli connection, looking at this very simple question of finding a formula for the sum of the kth powers of the first n minus 1 natural numbers. And we keep using this again and again because as we study and explore this formula, more and more information is given to us about the nature of Bernoulli numbers. So we write the formula sk of n in terms of the I equals 0 term and the other one. So k is even, keep in mind that. So k minus 1 is odd, and therefore the summation can start, the second part of the summation can start from 2. So we can write sk of n as bk of n times this extra stuff. And the sum, the second part of the sum is actually p integral by what we had proved earlier for p bigger than or equal to 3. And again, here, p to the I minus 2 is at least 3 to the I minus 2, and it's bigger than I plus 1. Therefore, if I look at the p-adic expansion of p to the I minus 2, there it is, p-adic expansion of p to the I minus 2, that's it. And then if I look at the p-adic expansion of this, it has to have fewer digits. This has I minus 2, or I minus 1 to be precise, digits, and this has to have fewer digits. So if a number a is less than or equal to b, you're trying to express a and b in terms of p-adic expansions, the number of digits of b must be more than the number of digits of a. And we argue for p bigger than or equal to 5, and then tidy it up for 3. I'm not going to go into all these itsy-bitsy details, but I'm sure all of you can follow these. These slides will become available afterwards, but once you get the idea, you can fill in the details. So this is basically the proof of this theorem. So multiplying the equation by vk and recalling what 6 actually divides v sub k, we see that this also is p integral, is 3 integral. Therefore, we finally finish proving this congruence. Okay. So the theorem is proved. So this is basically the proof of this beautiful congruence. I'm emphasizing the elementary nature of all these theorems. You have to understand that these elementary remarks coalesce into a profound interpretation much later. Now, in 1889, Voronoi proved an interesting congruence which has no Bernoulli numbers in it, and his theorem is that if you have a natural number and a and n are relatively prime, then a to the k minus 1 sk of n is congruent to k times n a to the k minus 1 plus summation j equals 1 to n minus 1. This greatest integer function is used, ja over n, j to the k minus 1. And this is actually a very simple proof. Let's just see how we will prove it. Well, for each j, we look at the number ja, and ja we divide out by n, we'll get a remainder qj and a remainder rj. We'll get a quotient qj and a remainder rj. We talked about this before. And what is qj? Well, qj is the greatest integer of ja divided by n. That's how you divide a number by n. And so I can take ja and raise it to the kth power, and that would be qjn plus rj to the kth power. But then because all these terms with n squared and higher powers of n can be ignored because I want to look at this thing mod n squared, I only need to look at the first 2 terms of that expansion, rj to the k and k qj n times rj to the k minus 1. And then keeping in mind that that basically Rj is equal to JA minus QJN, we may as well ignore that, and so put the n is minus QJN is irrelevant because it'll combine with this one here. So you may as well substitute JA there, and then you end up getting this result. Now, as J ranges over the integers from 1 to n minus 1, so does Rj, because A and N are relatively prime, and therefore summing the above congruence from J equals 1 to n minus 1 gives the result. This is Voronoi. I mean, this is, by the way, Voronoi apparently was 15 years old when he discovered this particular theorem. So we now combine these with our earlier result that when you have K even, and VK SK of n is congruent to UK n mod n squared. So what am I trying to do now? In the previous result, we had a congruence establishing a relationship between the numerator and the denominator of the kth Bernoulli number, mod n squared. And in this one now, we have a congruence with SK of n. We can combine both of them and then find that, for example, if you just multiply by VK of both sides, the Voronoi congruence, you essentially get this corollary. A to the K minus 1 UK is congruent to K VK AK minus 1 plus this summation. Very nice fact. And then we have Adams congruences and Kummer's congruences. Let me just discuss these. Adams congruence is the following. If P minus 1 does not divide K, then BK divided by K is in P integral. So before, we were trying to show P times B sub K is P integral. But now we can say that when I divide out by a K, this is still P integral as long as P minus 1 does not divide K. So remember, I kept telling you the denominator of the Bernoulli number has to do with the primes, is composed of primes P, such that P minus 1 does divide K. But if you stay outside of those are the kind of like the poles of the Bernoulli number. If you stay away from those poles, then BK over K still is P integral. So let's recall our previous result. And if you now say, what is the highest power of P that can possibly divide K? Let's say it's P to the T. Then we can apply corollary 2.10, with n equals P to the T, and we deduce that because n equals P to the T, we see that A to the K minus 1 is congruent to 0 mod P to the T, because we're assuming that K is divisible by P to the T. So this K is right there, okay? So choosing A to be a primitive root mod P, we can ensure that P is co-prime to A to the K minus 1. And so UK must be divisible by P to the T. So that's how we end up showing that if P to the T divided K, it also divided U sub K. And therefore, this still is P integral. So now the stage is set. The stage is set for what can be considered one of the remarkable achievements of Ernst Kummer, called Kummer congruences. This will, of course, be related later on to whoever the student was asking this question about regular primes. I will talk about that. But this will lead up to this idea that you can now consider whenever K and K prime are congruent mod phi of P to the E, then 1 minus P to the K minus 1 BK over K is congruent to 1 minus P to the K prime minus 1 BK prime over K prime mod P to the E. Now, this may look like a weird congruence, and why would you do this? Why does it look like this? But even Kummer did not realize the significance of perhaps his achievement, and it only comes to light when you think in terms of p-adic metrics. See, what does K congruent to K prime mod phi P to the E mean? If E is really humongous, what does it mean? It means K and K prime are very close p-adically. And then whenever K and K prime are very close p-adically, then essentially BK over K and BK prime over K prime are close p-adically. That's basically what's going on. And this should strike a note in your consciousness because of your training. What is the uniformly continuous function? Whenever x and y are close, if f of x and f of y are very close. We say f is a uniformly continuous function. So you can see immediately these congruences can be interpreted p-adically in terms of continuity. So that's what I'm saying. Notice what the theorem is saying using our p-adic metrics. So now I'll come back to that idea, and I'm just trying to put that in your subconscious so that it can incubate there, and then give you some insight into the knowledge later on. So let me prove Kummer's congruences. We want to prove that whenever k is congruent to k prime mod phi p to the e, then this function 1 minus p to the k minus 1 bk over k is close to 1 minus p to the k prime minus 1 over bk prime over k prime. Now, by the way, one more point. Not only can you interpret this p-adically, as I just mentioned, and think in terms of continuous functions, but you can also think of bk over k, if you remember, was essentially zeta 1 minus k, right? So it's telling you that zeta 1 minus k and zeta 1 minus k prime are close together. And this is the kind of intuition that certainly will not come through any form of chat GPT, previous knowledge. It's a leap of the imagination where somehow you realize there's a p-adic world out there, and this is completely new. This is a 1965-64 discovery by Leopold and Kubota, that you can interpret this as an interpolation of the p-adic zeta function. So now let's try to prove this. Go back to the 19th century, and let's just prove with our bare hands using elementary number theory, this theorem. So recall bk is uk over vk. And then we had this Voronoi congruence. And so let T be the power of P that divides K. And then if we set N equals P to the E plus T in our formula 2.6, we get A to the K minus 1 times UK is congruent to K, VK, A to the K minus 1, plus this summation. Okay, fine. Now, since P minus 1 does not divide K, that's part of the hypothesis, P minus 1 does not divide K. So we're away from the poles of that Bernoulli number. You see, that's the idea here. We're away from the poles of the Bernoulli number. VK and P are co-prime. And by the Adams congruences, BK over K is actually P integral. And so if BK over K is P integral, P to the T must divide UK. So because P to the K must divide UK, we see that immediately that from here, yes, from here, we can move back into this, A to the K minus 1 over A to the K minus 1 BK over K times U sub K is congruent to where are we here? Yes, basically what I'm doing here is I'm looking at 2.6, and I'm looking at 2.6 with N equals P to the E plus T, as I just said here. So here it is. And then now, because P minus 1 does not divide K, there's no problem. VK is only supported at primes. Divisible P, that's a P minus 1 divides K. Therefore, I can divide by V sub K, and P to the T divides K here. So I can divide out by P to the T, so you get this particular congruence. Okay. So we've shown that AK minus 1 BK over K is congruent to this particular summation. And so we're going to prove this now by induction. We'll begin with the case E equals 1. On the right-hand side of the above congruence, we can omit those J's divisible by P because E is equal to 1. Every time J is divisible by P, it's 0. Since K is congruent to K prime mod P minus 1, we see that J to the K minus 1 and J to the K prime minus 1 are congruent mod P by Fermat's little theorem. So choosing A to be a primitive root, we deduce that we can cancel the bk, the a to the k minus 1s. We deduce that bk over k is congruent to bk prime over k prime mod p, whenever k and k prime are congruent, mod phi of p, because we're looking at the case e equals 1. Now, when e is bigger than 1, we write our summation on the right hand side here into two, decompose it into two parts. The first part is when j is coprime to p. The second part when j is divisible by p. And the congruence 2.7 up there with e replaced by e minus 1 gives, for k equals 2, remember, I'm trying to prove this by induction, so I can assume that the formula with e replaced by e minus 1 is valid. So you put that down. And then when you subtract the two, you end up getting this particular fact, which we already proved. Subtract 2, you end up getting that 1 minus p to the k minus 1, a to the k minus 1 bk over k is equal to a to the k minus 1 with summation j and p coprime. Okay. So for k congruent to k prime mod phi p to the e, we deduce that congruence. So the proof is not complete. So I hope people realize that the proof of the Kummer congruence is very simple. And it's elementary number theory. But now, coming to the question the student just asked, we want to relate Bernoulli numbers to Fermat's last theorem. This is certainly the remarkable contribution of Kummer. Pierre de Fermat, I think many of you know, 1601 to 1665, was a lawyer by day and an amateur mathematician by night. And he made many conjectures in number theory, the most famous being this marginal note called Fermat's last theorem. And of course, it was solved in 1995, the culmination of major developments of 20th century mathematics by Andrew Wiles. Everyone knows this. And so the proof of Fermat's last theorem, using the complete arsenal of 20th century number theory, was certainly a tour de force, no doubt about that. Was this the proof that Fermat said he had in mind? Probably not. Theory of automorphic forms representation theory, Galois representations, modular forms, all these things are needed in proving Fermat's last theorem, and certainly Fermat was certainly not aware of any of those things. But he did claim that he had a proof, and many amateur mathematicians continue to try to reconstruct that proof, and it's questionable whether Fermat actually had a proof of his theorem. I said that once, and one of my students was saying, wait a minute now, wasn't Fermat a lawyer? And I said, yes, he was a lawyer by profession. Yes, that's true. Then aren't lawyers dedicated to the telling of the truth? And I said, no, not the way we see it these days. So he thought that since Fermat was a lawyer and he was dedicated to telling the truth, lawyers are dedicated to telling the truth, he must have had a proof. That is a dubious argument for sure, given the state of the modern world, and probably the world at that time too. Certainly not the case. What Fermat may have had is a proof in the case p equals 4. So a century before Wiles, Kummer connected Fermat's last theorem to Bernoulli numbers, and this is an interesting connection, which we will briefly describe. So prime p is called regular if p does not divide the numerator of the Bernoulli numbers b zip k with k even, and k is less than or equal to p minus 3. So p is a prime, and if p does not divide the numerator, that is the u sub k, of all these Bernoulli numbers b sub k with k less than p minus 1 over p minus 3, then we call it regular. And Kummer proved that if p is a regular prime, the equation x to the p plus y to the p equals a to the p has no non-trivial integers. So Fermat's last theorem is true for a regular prime. Now, it's still an open problem to show if there are infinitely many regular primes. A prime is called irregular if it is not a regular prime. Good definition. And using Kummer's congruences, we can show that there are actually infinitely many irregular primes. So this is an interesting contribution of Ernst Kummer. I mean, he spent a whole of his life doing work on Fermat's theorem, but in the process of trying to prove Fermat's theorem, he certainly discovered algebraic numbers or ideal numbers. But it's interesting to note that Kummer is not the person who came up with the theory of ideals. He only came up with the theory of ideal numbers, and that somehow you had to go away from numbers into ideals and talk about ideal factorization instead of factoring numbers. That idea actually is due to Dedekind, who was contemporary of Kummer, but it's certainly not Kummer's idea. So this kind of fixation, as it were, to this visual approach to mathematics, where you're trying to see things in as numbers or points on a line or something, is problematic. And abstraction seems to be the only way the mind can leap forward to higher realms of thought. This limitation of visualization is an impediment. So let's go back to Euler's formula for zeta 2k, which will actually figure into this proof that there are infinitely many irregular primes. So you will recall Euler proved zeta 2k has this beautiful connection with Bernoulli numbers. Now, as k goes to infinity, zeta 2k goes to 1, therefore gives an asymptotic for the behavior of the kth Bernoulli number. These Bernoulli numbers become humongous very quickly. And if you look at the formula, Euler's formula teaches us that the 2kth Bernoulli number is actually 2 times 2k factorial divided by 2 pi to the power 2k. And using a very elementary inequality, namely that e to the k is bigger than k to the k over k factorial. How do you see that? Well, if you expand e to the k as a power series, one of the terms is k to the k over k factorial. So you get this remarkable inequality for cheap. It's almost like Stirling's formula without doing any work. Then you end up getting this inequality that b sub 2k is bigger than k over pi e to the power 2k. So it grows really very fast. And certainly bk over k also grows very fast. Even so, if you just, it's like it's growing, bk is growing like k to the k. And so if you divide by k, you're not doing really very much. So bk over k also is growing very fast. And this will play an important role in our proof of the infinitude of irregular primes. So let's now try and prove that there are infinite many irregular primes. Suppose not. This is very reminiscent of Euclid's proof of infinitude of primes. Suppose not. P1 and P2S are the set of irregular primes. Then you form not the product. You know, in Euclid's proof, you
We are not able to hear you.
Oh, you're not able to hear me? Can you hear me now?
Yes.
Maybe I should. Okay,
Yes,
whenever I think whenever I move away from the computer, I probably am not audible. Okay, I'll try to stay close to the computer. So you have this number n, which is going to be p1 minus 1 to ps minus 1 times k. K is just going to be a parameter. And we'll just set n equals k. And we know that this number b sub n over n goes to infinity by the previous slide. So we can choose k so that b sub n over n is actually bigger than 1. And so let p be a prime so that p divides the numerator of bn over n. And by the Wannstedt-Clausen theorem, p minus 1 cannot divide n. And because p minus 1 cannot divide n, it cannot be any of the pi's. And therefore, this is not one of the irregular primes. And I want to show that this p is actually irregular. And the idea is, by Kummer's congruences, b sub n over n is congruent to b sub n m over m, where m is smaller than p minus 1. since p minus 1 does not divide, and m is even because n is even, and by the Kummer congruences, you get bn over n is congruent to bm over m, and so it must divide the numerator of b sub m over m also, and therefore it must divide the numerator, and therefore p is an irregular prime. It's a new prime, which was different from the earlier ones. And I think this argument can be fine-tuned to show something like the number of irregular primes is bigger than log x or something like that, up to x. So anyway, that's I think people have done things like that. Now, the cute application of Kummer congruences. Now let me discuss the p-adic series. Last time we discussed the convergence test for p-adic series. And we proved that a p-adic series summation Cn converges if and only if the nth term goes to 0. This is a very curious result, curious fact. And this convergence test can be extended to discuss convergence of double series. I'm just going to flash this, not make too much of it, because it's very simple. Again, you can have a double series, and as long as we have some sort of uniformity in the way these things go to 0, you can get that this solves the convergence in the usual way. So I'm just going to flash this and let it be, not make too much of a point on this issue.
Sir, here I have a question. So
Yes,
this
yes.
limit, these limits are taken with respect to p-adic metric, or?
Yeah, no. There's exactly. So it's a sequence, right? A sub n is a sequence, and when I say yes goes to 0, it's always a p-adic metric.
P-adic metric. Okay, thank you.
Yeah. You're absolutely right. Sorry, it's always a p-adic metric. Okay, so we now have this theorem about convergence of double series. So you see, the point is that these numbers are in this p-adic field. And so when we talk about going to 0, it's always with respect to the p-adic metric. And now so you can interchange the double series. And as in the case of real series, one can consider power series, summation a n x to the n. And just as in the case of power series, you have radius of convergence tests. Similarly, you have this same thing here. And everything goes through mutatis mutandis. And you can see that the radius of convergence can be now given by 1 over lim sup of the absolute p-adic absolute value of a sub n, 1 over n. So this is very much reminiscent of the classical calculus formula for the radius of convergence with the usual absolute value, and the same thing will work with the p-adic absolute value. Now, this begins, now that we have this understanding of this p-adic world, we can ask ourselves, well, are there analogs, p-adic analogs of functions we've been familiar with? For example, the p-adic, what about the p-adic analog of the exponential function? So in real analysis, the power series for x converges for all values of x. And in the p-adic case, this is no longer true. So you can still consider this series and now ask, where does this converge p-adically? And so in order to do that, you have to analyze the power of p that divides n factorial, because power of p that divides x is easy to figure out. And this is a famous formula of Legendre, where you kind of get your hands on this. And I'm not going to do all the itsy-bitsy details. These are very routine, and leave it to you that you can now, using this fact that the power of p that divides n factorial can be given by this formula, and using these estimates, you can show that the exponential function converges as a function of a p-adic variable in a smaller disk. Notice that p is a prime, p to the minus 1 over p minus 1. This is less than 1. This is always less than 1. And so it converges, but it converges in a very small disk, and the p is getting smaller and smaller. P as p gets bigger and bigger, by the way. So you get p to the log p over p minus 1. E to the log p over p minus 1, that goes to 1. So they are getting bigger and bigger, but the disks are strictly less than 1. And you can actually show all this stuff, that whenever x and y are sitting inside D, x plus y is also inside this disk D, because of the stronger inequality. Remember, we talked about the ultrametric triangle inequality, which is stronger than the usual triangle inequality. It's absolute value of x plus y is less than or equal to the maximum of the absolute values of x and maximum y, right? So, and then again, because of this fact, you can have the usual formula of exponential x plus y is equal to exponential of x times exponential of y. And by contrast, we can consider the logarithmic function. You remember minus log of 1 minus x is summation x to the n over n. And now we may want to consider this p-adically. So I'm putting this subscript p, not log base p, but rather log p-adic log. I want to interpret the power series as a p-adic power series. And this converges in the larger region of mod xp less than 1. And this is also, again, easy. We have to analyze the power of p that can divide n. And as elementary number theory will show you, the power of p that can divide n is at most log n over log p. And the convergence now is pretty easy to check. Okay, so we can do that. And so this actually converges as in this disk x minus 1 less than 1, p-adic absolute value. Okay. Now here's an interesting result. Now that we've at least introduced the p-adic logarithm and the p-adic exponential function, we get that summation 2 to the n over n. Of course, it diverges as an ordinary series. But if I consider it as a p-adic, 2-adic series, it converges. And the question is, what does it converge to? So if you just ignore rigor for a second and put x equals minus 1, you'll see it's actually, you can just put 2 in the previous formula, and log of 1 minus 2 is log of minus 1. And so this is what it should be. And as I mentioned, the exponential of x plus y is equal to exponential of x times exponential of y. Similarly, log of x times log of y is equal to log of x plus log of xy is equal to log of x times log plus log of y. So similar formulas work, and you can now try to find out what log of minus 1 would be in this case. And by doing this silly calculation, minus 2 log minus 1 as minus log of minus 1 squared, and you end up getting it's 0. So for each integer, what does that mean? So it's a kind of a curious result, isn't it? We have that summation to the n over n equals 0. And how did we get that? We're getting that by, this is telling me that, how do I interpret this result? It interprets the partial sums are divisible by arbitrary powers, arbitrary high powers of 2. It's getting closer and closer to 0. Therefore, this is a very counterintuitive thing. You can't guess this. You could certainly, very difficult to do it using elementary number theory, but this is a fact. The fact that if you look at these fractions and you just add them, and you can find an n such that this numerator is divisible by 2 to the n. That's I think it's a very interesting result. So what I'm trying to say is, by moving to this p-adic world, you're able to get information about ordinary numbers that you wouldn't have been able to get with your usual perspective. So now that we have looked at exponential series, the logarithmic series, maybe we can look at the binomial series and binomial expansion. And as you know, the binomial series is usually given by binomial coefficients, where you don't interpret a, choose n as a binomial coefficient, but rather as a times a minus 1, a minus n plus 1 over n factorial. And when you do that and you ask yourself again, where does this thing converge? You analyze that, and it turns out that it will actually converge for mod x less than 1. So the binomial series actually converges in the mod xp less than 1. And we'll now use this binomial expansion series to construct what is called the Artin-Hasse exponential function. So the exponential function I introduced last time in analogy with the classical exponential function, there's another function which has been very useful called the Artin-Hasse exponential function. And in order to explain this, I need to review the theory of the Mobius function from elementary number theory. Recall this function mu of n is defined as follows: mu of 1 is 1, and mu of n is 0 if square of a prime divides n. And if n is square free and composed of distinct prime numbers, its value is equal to minus 1 to the power r. And the important property of the Mobius function is this summation d divides n mu d is always equal to 0 unless n equals 1, when in case it's 1. And now we're going to set f of x to be this infinite product. Don't worry about convergence here. Just play with it like Ramanujan would play with it, or Euler would play with it. So product n going from 1 to infinity, 1 minus x to the n, and the power is going to be minus mu of n over n. And if you take logarithms, rearrange terms, and use this identity, you will find that it just turns out to be exponential of x. So f of x actually equals exponential of x as a formal identity. Now, the nth factor in the product converges in the region provided n is coprime. So this suggests we should actually consider a kind of a restricted product. And each of the terms now here, each of these terms, we will interpret using the binomial series. And the binomial series converges in this disk mod p mod x less than 1. And the infinite product makes sense as all the coefficients are actually p-adic integers. Thus, the series that's obtained from this product, I'm not going to do this exercise, because you have restricted n to be coprime to p. This shifting function now turns out to be 1 if n is a prime power of n is power of p, and 0 otherwise. And when I put the condition n and p are coprime, it'll only pick out the powers of p. And when it does that, you actually end up getting this remarkable function, which is called the Artin-Hasse exponential function. And what is curious about it is the Artin-Hasse exponential function has p integral coefficients. And when you check what are the coefficients of x to the p in this expansion, I will leave it as an exercise for you to do. It turns out to be 1 over p factorial plus 1 over p. And when you take common denominator here, you get 1 plus p minus 1 factorial divided by p factorial, which has to be p integral because I just constructed this function, which is p integral. Therefore, this must be divisible by p. So this is a kind of a very complicated proof of Wilson's theorem, no doubt about it, but it's an important point nevertheless. Now, I want to kind of conclude this particular lecture by discussing what's called Strassman's theorem about the number of zeros of p-adic power series. This is an important theorem which gives us an upper bound for the number of ZP zeros of p-adic power series. In fact, the argument can be generalized to treat zeros in larger disks as well. You don't need to just count p integral p-adic integers ZP, but you can also allow for denominators. So Strassman's theorem says that if I have a power series f of x summation a n x to the n, and the a-n's are p-adic numbers, and supposing, of course, in order to converge, you have to have a-n going to 0 in p-adic norm, and f of x converges for x in ZP, then let's define capital N by these following conditions. So the p-adic absolute value of a sub n has to go to 0. So it must have achieved a maximum at some point, right? So this is going to 0. Therefore, there must be a point where you attain the maximum, capital N. There must be some index. And of course, a sub n p is strictly less than a sub n p for n bigger than that point. So there must have been a point where you've achieved the maximum. From then onwards, it's actually going down. Then the theorem says that the function, this power series here, can have at most capital N zeros. So it's giving you a bound for the number of zeros. And the proof of this is not hard again. As I said, p-adic analysis is not hard. You just have to wrap your mind around this new metric. And most of the proofs are elementary number theory. So it's a kind of a nice way to take your knowledge of elementary number theory and move it into this p-adic world. So we're going to try and prove this theorem by induction on capital N. So that's the theorem. So we induct on it. When capital N is 0, what does that mean? It means that the maximum is attained at the very first coefficient. So if now suppose we have a 0, R is a 0, then f of R is 0. So I can take the A0 term, move it to the left-hand side, and I get things like this. And so the absolute value of A sub 0 P is bounded by the maximum of these guys by the strong inequality. Remember the strong triangle inequality? Yeah, you get that. So you get this inequality, and this is a contradiction to what we just said right there. So there are no zeros. So in other words, if the in Strassman theorem, the maximum is attained at the very first coefficient, then there are no zeros. It's an interesting theorem. And now let's assume that n is bigger than or equal to 1. If r is 0, we can write it as f of x, and f of r is 0, so same as f of x minus f of r. And then we write the power series and factor out x minus r. And then now you can see why I was adamant about discussing double series, because I need to use that theorem. And we can rearrange the thing and write it as x minus r times summation bn x to the n, where the bn's are, of course, given by the summation a n plus 1 plus k r to the k. And this particular coefficient, b sub n, satisfies the following inequality, again by the strong ultrametric triangle inequality that we discussed for the p-adic case. And because the maximum is being attained at a sub n, we know that this has got to be less than, b sub n has to be less than an, capital N. And that bn minus 1 is the formula with a sub n plus 1 r dot dot dot, and again by the same strong ultrametric inequality we get this. So we have that b sub n p is bounded by mod an p. And now if I were to consider g of x to be f of x divided by x minus r, then what happens? This satisfies the hypothesis of the theorem with capital N replaced by capital N minus 1. That means now the maximum is occurring at capital N minus 1. And this has at most n minus 1 zeros. So by induction, we're done. So this is the proof of Strassman's theorem is very simple. You just have to wrap your head around the p-adic metric. Now, one use that we can make of Strassman's theorem is to count the number of zeros of the p-adic logarithm function that we discussed just earlier. Log of 1 minus x equals summation x to the n over n. One cannot use Strassman's theorem directly. We need to modify our function a little bit. So we do that. So we'll change the function to px. And then we do that, then it becomes log of 1 minus px and summation p to the n x to the n over n. And now we can see if p is not equal to 2, we can see that the maximum of this thing is actually attained at n equals 1. And therefore, this function has at most 1 0. But x equals 0 is 0. And so we deduce the only p-adic zeros of log of 1 minus px is x equals 0 for p not equal to 2. And for p equals 2, we see that if you calculate this bound, you see that it has at most 2 zeros. Now, x equals 0 is a 0, but x equals 1 was are the 0, because that's what we found in summation 2 to the n over n. Remember that example I just gave you a few slides back? That summation 2 to the n over n actually was 0. So that must have been the other 0. So we now get an interesting insight into the number of zeros. Now, we can continue this kind of trying to extend our foray into the p-adic world by trying to take whatever we know in real analysis and seeing if we can transport the structure, to see whether or not this carries over to the p-adic world. So now that we have discussed a little bit of continuity of p-adic functions, we may talk about derivatives. And so here, the p-adic derivative is defined with you have to have a sequence going to zero. So p of the n goes to zero p-adically. And so it makes sense to make the following definitions. If I want to talk about the derivative of the function, I would take f of x plus p to the n and subtract f of x and divide by p to the n and take the limit. Again, the limit is a p-adic limit. Okay, keep that in mind. So this would be, when this limit exists, we'll call it f prime of x. And now with this particular new definition, you may want to ask, okay, let me differentiate some things I know. F of x equals x to the n. And you differentiate it, it turns out to be n times x to the n minus 1. Now, the proof of this is not the way you prove it normally. So I ask you to do it. Do it yourself, and you'll see that the ordinary proof is not what you really have to deal with this p to the n stuff. And it's again, congruences are essentially p-adic analysis. So I'll leave that as an elementary exercise. So thank you very much for your attention, and let's seek the blessings of Ganesha. This is the scene at Kanchipuram Temple, Tamil Nadu. Okay, so voila, that's the end of the lecture.
Madam. Hello.
Yes. Yes, sir.
Yeah, any questions, please?
Thank you very much, sir, for the Strassman's theorem. Sir, I have one question. Strassman's theorem, one sees only in the context of p-adic analysis, means p-adic numbers. Is there a theorem for real numbers? Because when we teach power series only in complex analysis, sometimes we see zeros only of specific functions. We don't, at least I have not come across a theorem which gives bounds on the number of zeros. So,
yeah, in complex analysis,
maybe there.
Yes, in complex analysis, you get theorems, Jensen's theorems, and things like that, which give you bounds for the number of zeros in a disk, right? Jensen's theorem gives you have an analytic power series, and it gives you bounds on the number of zeros in a disk. So in the case of complex analysis, we really have to talk about zeros in the disk. And there are some theorems due to people like Laguerre and other theories that talk about real zeros of power series. There are theorems like this. So this is all the work of Polya and other people. Yes, you're absolutely right. Unfortunately, we don't teach many things. You see, that's a very good point, Anuradha, that you're making. In many ways, you see, certain books get standardized, and the treatment of subjects becomes kind of routine and pedantic, but there are many that was based on choices, perhaps choices of convenience, that things get into certain shapes. But there are, as you correctly point out, there are people who have been looking at the analogs of Strassman's theorem. I mean, there are, before Strassman, there have been people who have been looking at the number of zeros of power series, and Jensen being one of them, Polya, Laguerre, and other people. They have been looking at these things. Does that answer your question?
Yes, thank you.
Okay.
Thank you.
I have a small question, sir. Usually we define a prime to be regular. P doesn't divide the class number of the field Q zeta, where zeta is a primitive pth root of unity. Of course, I think Borevich books prove that two are equivalent. The definition that you gave in terms of the numerators of Bernoulli numbers. But I don't know. It's a long equivalence. It's not so easy to prove.
No.
It's not so easy.
Well, yes and no. Let me firstly, Professor Kanduja, very happy to hear your voice. I trust you're doing well. It's always nice in this modern age that we can get to meet on this global chat. The other point with respect to, yes, hi, yeah, nice to see you. Yeah. So the what you're talking about, the class number formula, goes via the fact that the L1 chi can be written in terms of the Bernoulli numbers.
Yes.
And that's the class number formula. Yes, I didn't want to go there, of course, that requires more mathematics. But you're absolutely right. So Kummer gave that formula, and so the prime P not dividing those Bernoulli numbers is tantamount to saying P does not divide the class number of the.
Yes.
Yes, you're absolutely right. Yes.
Hi, sir. I have a question. Am I audible?
Yep.
Hello.
Yep.
Is the upper bound on that theorem always attained on Strassman's theorem?
Yeah, it is. Like we just discussed right now.
So for any series, you have exactly n roots. Is that a known result, or do we expect it?
No. When you say is it attained, there are examples where it's attained. It may not be for any general series.
Okay. So do we have examples where it is not attained also?
I think so. I think you may find a few of these examples in Gouvea's book on p-adic numbers. Is that Krishna Arjun that's asking this question?
Yes, sir. Yes, sir.
Oh,
We met
hi.
at HRI. Hello, sir.
Yeah. Oh, yeah. Hi. How are you doing?
Yes, sir. I'm good.
That's good.
Okay, sir.
Hello, sir. I have a question.
Yeah.
Am I audible?
Yep.
Sir, I have a doubt in that Adams congruences. You told that if p minus 1 does not divide k, then b k by k is p integral. Bk is the Bernoulli number. Can we improve upon this and say that bk over k is always p integral? Because in that last class, you told that minus bk over k is zeta of 1 minus k. This side is always a negative natural number. So bk over k is always p integral, irrespective of p minus 1 divides k or not.
No. It can't be, because you see, what did the Won-Stout-Clausen theorem tells you that bk has a denominator. It's divisible by, it's a square-free denominator. Bk is square-free, and it's divisible by the primes p such that p minus 1 divides k. In particular, p equals 2 divides it. So it's not, bk is not 2 integral. And 3 divides that, because when k is even, it's not 3 integral. So no, this doesn't, you have to assume p minus 1 does not divide k.
Okay, thank you, sir.
Yeah.
There is a question asked by somebody called as Vipin, and he says that how can we decide when will we get rational or irrational by adding rational infinite times? Like in zeta function, zeta 2 is pi square by 6, but there are other series which converge to rational.
Yeah. So we don't know anything about that. I mean, no one can say, just because you added you can add rational numbers and get a rational number. You can add rational numbers and get an irrational number. Both are possible. There is no theory to tell you which happens when, and that's what makes everything difficult.
Thank you, sir.
Oh, you're welcome. Yeah.
If I may ask the question, the Voronoi congruences are read only modulo n square. So are there congruences for n cube, n raised to 4 and so on, higher?
Yeah, good question. Very good question. And the answer to that is essentially yes, there are. You just need to keep track of those extra terms. Remember, I had the original formula. So you're talking about, say, something like higher Voronoi congruences. So let's say you wanted something modulo n cubed. If you look at that formula that we had earlier, you will see that sk of n was given by some polynomial in n. And so you will then have to look at the first 3 coefficients, and the fourth one, a higher, you may have to drop off, right? So you can develop a theory. It just gets a little messier as you go up. But it's a good question, and maybe one of your students can think about that if it's not already done. This is again an important point. When you ask a good question like that, I try to tell my students, do it. Don't go Googling this and then kind of discombobulate your brain in the process of Googling this thing. rather sit down and work it out yourself, and you'll see that even if whether it's done or whether it's not done is irrelevant. And then if it's done already, well, you discovered it yourself. And if it's not done, then you have material for a paper or something, right? So this is a nice way of doing research. But n cubed, yeah, I think it's a good question. It's probably worth doing.
Okay.
Yeah.
Okay. So I think there are no more questions. So let us thank Professor Ramamurthy for giving a wonderful lecture. Yeah.
Thank you so much, sir. Murthy sir and Chitra sir.
Hello.
Garge madam. Hello.
Yes.
Garge madam.
Yes. Yeah.
Sir, can I ask a doubt? Hello.
Okay, can ask.
Sir, like from our reals, right? Like we consider these sequences of reals and then we construct these hyper reals, right? And then it should be possible to do this for p-adics also, right?
Yeah, yeah. People do that. I mean, you can compute, for example, the p-adic numbers are not algebraically closed, and you go to the algebraic closure, and that's what's sometimes denoted as CP, which is the analog of the complex numbers. So you can keep on building extensions beyond that.
Thank you.
Yeah, you're welcome. Yeah.
Sir, may I ask a small question?
Yeah, go ahead.
Sir, this 691 is again an irregular prime, and related to that, there is a Ramanujan 691 congruence. So, can you shed some light on this irregular primes and congruences between modular forms? I mean, how these two are related?
Yeah. That's a good question. So now, if you know something about Eisenstein series, you see that, for example, the kth Eisenstein series has a Q expansion, and the first term is B sub k over k.
Yes.
So whenever you have a regular prime that means p divides the numerator of B sub k, let's say, then that constant term disappears modulo p. So you have a kind of a cusp form mod p. So regular primes give the classical Eisenstein series gives rise to a cusp form mod p in the case of a regular prime.
Okay.
In the case of an irregular prime, you have no problem.
Okay.
Yes. So yeah.
So there's an interesting question. Mrunal Hardikar is asking if QP is ordered field.
Not really. No, it's not an ordered field. No.
Hello.
Yeah.
Ramamurthy sir, thank you so much for today's lecture. You gave the nice lecture, Strassman theorems and Adams theorems, and furthermore, and nice interactions with the audience and on these things. I'm on behalf of the Department of Analytics. I'm so much, I'm very much thankful to you. Now I request the Garge madam conclude the session. Garge madam. Hello. Hello, Anuradha madam.
Connection. So guiding us in many ways. So we hope to see many more interesting theorems tomorrow. So thank you to all the participants, especially all the faculty members who have joined from various institutions, and see you tomorrow again for further lectures in this series. Thank you.
Well, thank you, everybody. Goodbye.
Thank you.